Hey everybody, in Calc BC, welcome to lesson 1.2, evaluating limits analytically. And if you're following along with the AP Calculus course and exam description, this is going to cover 1.5 and 1.6 from their version of Unit 1. Determining limits using algebraic properties of limits and determining limits using algebraic manipulation. And you can read more information about what these topics must cover as informed by College Board by visiting this page on Schoology. Just a reminder, there are 3 lessons in our version of Unit 1. The next one will cover some of these next topics. Yes, we are not going to be covering every single topic in Unit 1. Some of it is informing our future lessons and it will be covered automatically, and some of it will come back to in future review lessons as we get ready for the AP test. But right now we're just laying that foundation, making sure everybody remembers limits before we move on. All right, so I'm going to pause screen share for just a second. And here are our notes for 1.2. Again, these are on Schoology, so you are welcome to print these out yourself if you'd like. Or you can just write this on your own line paper. But remember, I am going to ask you to take photos of your handwritten work and turn it in. So make sure you're writing our notes along with us. So up at the top here, we have a whole bunch of properties of limits. And if we have 2 different kind of limit statements here, like a limit as x approaches c of f of x and a limit as x approaches c of g of x. And maybe we just say those values are L and M. And then we've got these pretty simple properties here. So we have a sum rule. So for adding the 2 functions, then the limit is just the sum of their initial solutions. Difference works the same way. Product rule works the same way. Quotient rule works the same way. Of course, we can't divide by 0. Constant multiple rule. So if we have this k, that's a constant that we're multiplying by something, the answer is just the limit times the constant. The power rule, also works the same way. We just raise the answer to the power. And the limit of a composite function rule. So if f and g are functions such that the limit as x approaches c of g of x equals L, and the limit as x approaches c of f of x is f of L, then the limit as x approaches c of f of g of x equals f of the limit of x approaches c of g of x equals f of L. Okay, so that, to me, I read that kind of quickly, and it seems a little bit like a crazy amount of notation. But it's really just talking about a composition of functions, so like an f of g of x, and the answer is similarly like you plug the inner in first and then the outer. We'll come back to that. So if that doesn't really click yet, don't worry about that. Let me look ahead. We will see a little bit of composition of functions in here, but even so, I don't think we need to worry about that definition too much. We'll come back to that if we need to, and if you want me to answer any questions about that, bring those to class and we can cover that, okay? But let's just get into some examples here. Given f of x equals x minus 5 and g of x equals x squared, let's evaluate the following. So the limit as x approaches 1 of f of x. So in the first lesson of this unit, we only found limits using a table or using a graph. Now we're going to actually use the equation. And letter A only uses f of x, right? So x minus 5, that's a line. There are no holes, there are no breaks. It's just your typical line. So the limit as x approaches 1 from the sides is going to be the same as the value of the function. So all we have to do is plug in 1 for x. So we have 1 minus 5, and it's going to be at -4. Right? And we could take a look at this graph. It's literally just a line, y equals x minus 5. Plug in 1 for x, and we would see the same y value, -4, okay? Letter B, the limit as x approaches 1 of g of f of x. Look at that, a composition of functions right off the bat. So what are we going to do here? So I would say let's plug in our f of x in the middle. So we have the limit as x approaches 1 of g of x minus 5. So f of x was x minus 5. I always plug in the inner first, and then let's plug in the outer. So we have g of x equals x squared. So our x that's defined there is being replaced by x minus 5. So what we really have here is the limit as x approaches 1 of x minus 5 squared, right? Because I'm replacing the x with the x minus 5. So g of x is x squared, g of x minus 5 is x minus 5 squared. And now we can plug in the 1 because there are no holes or breaks in that expression, so we can just plug in. It's called the direct substitution method, right? This is -4 squared, which is 16. So if our function doesn't have any holes or breaks, then we can just simply plug in, directly substitute to find the value of the limit, right? There's no difference then between the limit value and the function value. All right, so let's take a look at this next example. Limit as x approaches 2 of 3x squared minus 5x plus 1. That's a pretty standard polynomial. No holes, no breaks, so we can just plug in 2. Uh, 3 times 2 squared, so 3 times 4 is 12, minus 10 plus 1 is going to be 3. Next example, the limit as x approaches 5 of cosine of pi x over 6. Okay, so thinking about our cosine graph, it's a cosine curve, it just kind of bounces up and down, right? There's no holes, no breaks. So we should be able to just plug 5 in for x. That just means we're looking for the cosine of 5 pi over 6. So this is going to test our unit circle memory. Maybe you remember, hopefully, the cosine of 5 pi over 6. So we're looking for the x value at the angle 5 pi over 6 on the unit circle. And that value is -√3 over 2. We do still need to know that unit circle, so we're going to pull that back out if we need to. And I may test you on that in class at some point. It won't be like a pop quiz, though, don't worry. If we cannot evaluate a limit by direct substitution, sometimes we can use algebraic techniques to rewrite the function so that we can evaluate the limit. All right, so let's take a look at this. If we try to plug in -3 right away, what happens? We get 9 minus 3 minus 6, so 0 over -3 plus 3, 0. 0 over 0. Now that's not a solution, right? We can't divide by 0, first of all, and 0 over 0 is never going to be the answer to the limit. So we can use algebraic techniques to simplify this. So what we can do in this case is we're going to try to factor the numerator. And it turns into x plus 3, x minus 2 over x plus 3. And the x plus 3's can cancel, so we get the limit as x approaches -3 of x minus 2. And then we can follow up using direct substitution. So we can plug in the -3 for x, and we get -5. All right, so I want to be very clear. The graph of the function x minus 2 is not the same as the graph of the function x plus 3 times x minus 2 over x plus 3, right? This graph has a hole at x equals -3. This graph does not. But for the purpose of limits, we can say that this statement is equal because the limit is going to be the same, right? Just the fact that we filled in a hole and there's no hole anymore doesn't change the value of the limit, right? That actually helps us to use direct substitution. Okay, so that's that example. Let's keep going. All right, next up we have the conjugate pair method, which is common with square roots. So what we're going to do here in this one is multiply by the conjugate pair of the numerator, meaning we change this minus to a plus and multiply, and that'll help us to get rid of this. Because right now, if we plug in 4, we're going to get an indeterminate form, right? We're going to get 0 over 0. So let's try the limit as x approaches 4 of the square root of x minus 3 minus 1 times the square root of x minus 3 plus 1 over x minus 4 times square root of x minus 3 plus 1. Okay, so we're going to FOIL or distribute the numerator, and we're going to leave the denominator factor. So we have square root of x minus 3 times the square root of x minus 3, which is just going to cancel to leave us with x minus 3. The outer and the inner are going to cancel out, right? We have a positive square root of x minus 3 and a negative square root of x minus 3. That's the whole point of multiplying conjugate pairs, is that the outer and the inner always cancel. So then we're just left with the last, so -1 times +1, which is going to be -1 over, and again, I'm going to leave the denominator factor because that's not the conjugate pair piece. X minus 4, square root of x minus 3 plus 1. And so on top, this becomes x minus 4. On the bottom, we still have the same thing. While I'm writing this, just a reminder that you want to make sure that you're always writing the limit statement before your expression. That's something that's really common to miss. And if this happened to be a free response question on an AP test, you would get docked if you tried to say that this was equal to this without the limit statement, because that's just nonsense. That's not true. But it's just a very simple notation error that'll come back to bite you. So make sure that you're writing limit every time. And now hopefully you can see that these x minus 4s can beautifully cancel out. And we're left with 1 over square root of x minus 3 plus 1. Okay, so now we can try to plug in 4 again. It's going to be much nicer. And as soon as I plug in the 4 successfully, I don't have to write the limit statement anymore. So now we have 1 over square root of 4 minus 3 plus 1. So it's 1 over root 1 plus 1. 1 over 1 plus 1 is going to be 1 over 2. And that's our answer. So we successfully removed the hole. We removed the point discontinuity so that we were able to find the limit, right? On a graph, this would look something like a hole initially. This is just a made-up curve. I don't know what the curve actually looks like for this question because I haven't graphed it. But we are successfully removing that hole by canceling these x minus 4s out so that we can find the limit as if we're just plugging in the value. Okay, let's try the next one. The limit as x approaches 0 of 1 over x plus 2 minus 1/2 all over x. Okay, so this question looks a little bit bonkers. I think there are definitely multiple ways that we could do this. I'm going to start by finding a common denominator within the numerator. So I'm going to multiply the 1/2 times x plus 2 and x plus 2, and the 1 over x plus 2 times 2 and times 2. And let's see what happens. We end up with the limit as x approaches 0 of 2 over 2 times x plus 2 minus x plus 2 over 2 times x plus 2 all over x. And then we can combine this to 2 minus x plus 2 over 2 times x plus 2 all over x. And I don't like this fraction within a fraction business, so I'm going to start to try to remove that. So we have limit as x approaches 0. And 2 minus x minus 2. The 2 minus the 2 is going to cancel and leave us with a negative x over 2 times x plus 2 And I'm just going to multiply that by 1 over x. So I'm removing this over x and making it its own multiplied fraction, right? So if we're dividing by x, it's the same thing as multiplying by 1 over x. 2 minus x minus 2 became negative x, and this 2 times x plus 2 is still there. All right, so now the x's can cancel. This x up here and this x down here. So we're left with the limit as x approaches 0 of negative 1 over 2 times x plus 2. And I can plug in 0 for x at this point because I've officially removed the discontinuity. And since I'm plugging in 0, I'm not going to write limit again. So we have negative 1 over 2 times 0 plus 2, or negative 1 over 4. Boom, we got it. All right, next up, the limit as x approaches 3 of x cubed minus 27 over x minus 3. Okay, so for this question in particular, it would be helpful to remember a sum of cubes or difference of cubes factoring formula. And so that's why this hint is here. If you don't remember, let's write that down quick. So a cubed plus b cubed factors to a plus b times a squared minus ab plus b squared. A cubed minus b cubed factors to a minus b times a squared plus ab plus b squared. Okay, so here's how I remember this. You have to just remember that it's a and b and then a squared, ab, and b squared. But for the signs, I don't know if you've ever learned this before, but I always remember this by using the word soap. And so you think about the original sign that was in the unfactored version. So in this first one, it's a plus. So the first sign in your factored version is s, the same. The second one is opposite. And the third one is always positive. And in this second version of the formula, it's the same thing. It started with a minus, so the first sign is the same. The second one is the opposite. And the third one is always positive. So it goes same. Oh geez, this is going to be terrible. Opposite and always positive. Okay, so maybe you can write that a little bit nicer than I did on your version of the notes. But there you go. If you ever forget how to factor a sum or difference of cubes. All right, so my Zoom just crashed mid-question. Awesome. But let's get back to this. So what we were just saying is that you can use same, opposite, always positive to remember the signs for sum and difference of cubes. So let's get back to the question. Limit as x approaches 3 of x cubed minus 27 over x minus 3. If you plug in 3 right now, you're going to get 0 over 0. No good. So what we need to do is we need to factor the numerator using the difference of cubes. So our a here is going to be x. Our b is going to be what? 3, right? Because 3 cubed is 27. So a is x, b is 3. So we're going to write this out as the limit as x approaches 3 of x minus 3, x squared plus 3x plus 3 squared, which is 9, over x minus 3. And now the x minus 3's can cancel, right? So we're left with the limit as x approaches 3 of x squared plus 3x plus 9. And we plug in 3 for x's, and we get 3 squared plus 3 times 3 plus 9, which is 27, right? 9 plus 9 plus 9. There we go. Okay, so that's how we do that one. And I would say it's probably a good idea, just like it is to have the unit circle memorized, to have formulas like this memorized so you can factor quickly in the moment when you need to. Let's take a look at the next example. Find the limit as delta x approaches 0. So we haven't seen this symbol yet, but delta x usually just means like change in x in this context. We're going to just treat it like a variable though. Okay, so when it says x plus delta x, we're treating that like its own variable, kind of like it said x plus y or something like that. And if we have f of x equals 2x minus 5, you might recognize this as a difference quotient, right? We first cover this in honors pre-calc, and then you cover it again in calc AB, and now we're covering it again. So we've got to be able to plug in 2x minus 5 for both of these. So what I'm going to do here is, first, before we even get to the limit statement, just so that we don't have a confusing situation here, I'm going to write out f of x plus delta x. And we're going to figure that out first. So this means 2 times, wherever there's an x in the f of x formula, we're replacing it with x plus delta x. Like that, minus 5. So f of x plus delta x is 2 times x plus delta x minus 5. Just like if it said f of 7, we would plug 7 in for x. It's f of x plus delta x, so we plug x plus delta x in for x. And we can distribute the 2, so we get 2x plus 2 times delta x minus 5. And that's what we're going to plug into the limit statement. So now we return to the limit as delta x approaches 0. And f of x plus delta x we just found. So we're replacing this with this. So we have 2x plus 2 times delta x minus 5 minus f of x. And f of x is just our original statement. So 2x minus 5 all over delta x. We don't replace the delta x part. Now I'm going to see if we can cancel anything out. So we have 2x minus 2x. And we have negative 5 minus negative 5. Beautiful. That goes away. So we end up with the limit as delta x approaches 0 of 2 delta x over delta x. That is pretty nice. So now we have the limit as delta x approaches 0. And these delta x's cancel and just leave us with the 2. And now we have the easiest direct substitution problem in the world because there's not even a delta x to plug in for. So the answer is just 2 once we directly substitute because there was nothing to substitute in. So our answer is 2. Okay, so next up we're going to look at some limits that are fairly common in the calculus world and what their graphs look like. And these are going to come from trig. So let's take a look here. Use your calculator to graph y equals sine x over x. So I'm just going to do a basic rough sketch here if you want to on your calculator. You can graph this. So if we do that, we're going to get sine of x over x. I'm going to make sure that I am in radians mode. Ooh, I was in degree mode. Sine x over x, graph. And so what this is doing is it's kind of like a sine curve, but it's getting, it's approaching an asymptote of 0 as it keeps going this way and as it keeps going this way. So the curve is getting kind of smaller and smaller. The amplitude is getting smaller as we get further away from the y-axis. So if we do a rough sketch of that, I'm not even going to worry about the values on the x-axis, but basically we know that at an x value of 0, we would be dividing by 0. So there's going to be a hole here, and then the graph kind of does this. Something like that. So if we had to guess what the limit as x approaches 0 of sine x over x was, I think we can agree that the y value looks like it's 1, right? And you can confirm that if you take a look at the graph, but also if you look at the table of values as it approaches an x value of 0, you'll see that it's approaching 1. If we do the same thing for 1 minus cosine x over x, the graph is going to be fairly similar, but it's going to be more like a cosine graph. So there's going to be a hole here, and then it's going to kind of do this, like a cosine graph that's shrinking over time. So the limit as x approaches 0 of 1 minus cosine x over x looks like 0 to me. Okay. So that was kind of like a discovery. We looked at the graph. Now we are going to flip the page here. And this is some special trig limits that we should know, right? And this is coming straight from what we just looked at. So the limit as theta approaches 0 of sine theta over theta is 1. And for the cosine one, we have 0. And that's coming straight from the graph that we just looked at. And let me turn off my notifications. There we go. Then we have limit as x approaches 0 of sine of 5x over 5x. And so what we're going to do here is I'm going to think of letting theta equal 5x. So we can change this to yeah, we can change this to, I don't know if I want to do that. Yeah, we can do that. Okay. So we have the limit as x approaches 0 of sine of theta over theta, right? But the problem is my limit statement is still in terms of x. So if I want this to be in terms of theta, I'm going to figure out what is x equal in terms of theta. So x would be, if I divide it by 5, it'd be theta over 5. So I can change this to the limit as theta over 5 approaches 0, sine of theta over theta, and theta over 5 approaching 0, that's the same thing as theta approaching 0, right? So this is just going to equal 1. Okay, but that might have been a little complicated. There is another way we can think about this. If we think about it as the limit, let's go back to the beginning. The limit as x approaches 0, sine of 5x over 5x. We could think of this if we take out the 1/5. And this, the limit as x approaches 0 of sine of 5x over x. It's the same thing as multiplying 5 times this initial limit, right? Because think about the graph, it was at a height or a y value of 1. If we change the amplitude using this 5 here, it's going to change this whole thing to 5. So I don't really like the way that that worked out. I like this one more. This, we just kind of change it so that it looks like this original trig limit definition up here. And that made it equal 1. Okay, so I think we should stick with this one. But let's keep going. The limit as x approaches 0 of 5 sine of 2x over sine of 3x. Okay, so let's see what we have to do here. In order to make this look like these, what I'm going to do is say the limit as x approaches 0 of, I'm going to pull the 5 out in front. Then, in order to make this look like this up here, I'm going to say that the theta is the 2x, and I'm going to multiply by 2x over 2x. So we're going to have 2x times sine of 2x over 2x. So this is 2x over 2x, right? I can multiply by 5 over 5. It doesn't make a difference, right? Because that's just multiplying by 1. So I'm just manipulating this fraction by multiplying by 2x and dividing by 2x. I'm going to do the same thing in the denominator with the 3x. I multiplied by 3x and divided by 3x. And now I can calculate the limit by saying, first of all, these x's can cancel out. because there's one on top and one on the bottom of the larger fraction. And so we have 5 times 2/3 times this, which has a result of 1, just like we showed in example 1. And the denominator also has a value of 1. So that really equals what? 5 times 2 is 10 thirds. Okay? And let's take a look at this last one. The limit as x approaches 0 of 2x plus sine x all over x. So first I'm going to separate this fraction into 2 smaller fractions. I'm going to split the denominator. 2x over x plus sine x over x. And this becomes 2 different limit statements. So we have the limit as x approaches 0 of 2, right? Because the x's can cancel. And then we have the limit as x approaches 0 of sine x over x. The limit as x approaches 0 of 2 is just 2. The limit as x approaches 0 of sine x over x, if we look up here, that's going to be 1. So this answer here is 3. Okay, so I feel like I had a little bit of a hiccup explaining this first question here. Really, it's just if this value equals this value, the answer is just 1. That's what this trig limit up here is telling us, because we're still approaching 0, so it doesn't affect the final answer. The fact that there's a multiple on the top and on the bottom. Okay, so that's what's going on there. Hopefully that makes sense. If you have questions, bring them to class. That is the end of our 1.2 notes. Thank you very much. And don't forget to submit your completed notes on Schoology. Have a great day.